Welcome back to the deep dive. Today we're looking at something really quite fundamental, a major shift in how chemistry gets done. Discovery isn't just happening at the lab bench anymore, is it? It seems algorithms, high-performance computing, they're really guiding the way now. We're diving into how researchers tackled a chemical problem that's been around for decades. It involves ketones, some of the most common molecules out there, and our sources show how they used computation, really predictive computation, to find a shortcut around a big chemical hurdle, a shortcut for the whole field, potentially.
That's right. The hurdle involves ketones, yes, these incredibly common organic compounds.
Mm.
Chemists have, well, for a long time wanted an easier way to use their reactivity, specifically by turning them into something called kettle radicals.
Kettle radicals. Okay, and why are these so important? They're not just, theoretical constructs.
Oh, definitely not. They're highly reactive, really energetic intermediates. Think of them as vital building blocks. If you can control them, you unlock new ways to build complex molecules, things like natural products or, crucially, new drug candidates. So yeah, very high-value targets.
Right. But the difficulty comes down to which ketone you're starting with.
Exactly. It works okay, relatively speaking, for what we call aryl ketones. Those are the ones with specific ring structures, aromatic rings attached.
Okay.
But most ketones you actually encounter, in industrial processes, the real workhorses. They're the simpler alkyl ketones.
And those are the problem children, chemically speaking. Why are they so much tougher to work with?
It really boils down to electronic stability. Those rings in the aryl ketones, they help spread out and stabilize that radical intermediate after it forms.
Ah, okay. Makes sense.
Alkyl ketones don't have that stabilizing feature, so they're, let's say, electronically stubborn. For decades, trying to reliably make and use these alkyl kettle radicals.
Ugh.
It was tough. You needed harsh conditions, really specialized, expensive reagents, just not practical for doing things efficiently or on a large scale.
So the mission for the team at Hokkaido University's WPI-ICREDD was clear, even if it sounds simple. Find a mild, practical way to tap into these alkyl kettle radicals.
Deceptively simple, yes. And that's where they hit the wall initially. The Hokkaido group first tried a method using light photocatalysis. They took a palladium catalyst, combined it with a phosphine ligand, a common partner molecule, and used light to kickstart the reaction.
And this had worked before.
It had. They'd actually had success with this exact setup for the easier aryl ketones in their previous research.
But plug in the alkyl ketones, and nothing. Or not what they wanted.
Pretty much. The reaction just didn't go. It failed specifically for these alkyl ketones.
What was the mechanism? What stopped it?
The issue was a very rapid, self-sabotaging process. It's called back electron transfer, BEAT for short.
Back electron transfer, BEP.
Right. So think of it like this. The light excites the palladium catalyst.
Mm-hmm.
The catalyst then passes an electron to the alkyl ketone. A success. You formed the kettle radical you wanted. But because that alkyl radical is unstable, as we said, that electron it just received, it almost instantly jumps right back to the palladium catalyst.
Ah, neutralizing the radical.
Exactly. Before it has any chance to react further, so you're back where you started.
It's like flipping a switch on, but there's an immediate short circuit that trips the breaker every single time.
That's a great analogy. Yes. You momentarily make what you want, but poof, it's gone. Back to the starting material. And here's the critical part. The success or failure of these palladium reactions heavily depends on that phosphine ligand you pair it with.
The ligand controls the environment around the palladium.
Precisely. Its electronics, its shape.
Yeah.
It dictates how the palladium behaves.
Okay, so the team figured maybe the right ligand could stop that short circuit, could somehow prevent or slow down that back electron transfer.
That was the hypothesis. Find a ligand with just the right properties, electronics, spatial, to keep that electron on the ketone long enough for it to do something useful.
And this is where the sheer scale of the problem hits you, right? Because phosphine ligands, there are a lot of them.
A lot is an understatement. We're talking thousands, literally thousands known in the chemical literature.
Thousands, wow.
Each one slightly different. Now, imagine trying to test them experimentally, even a fraction, say a few hundred.
That would be years in the lab, synthesizing, testing, using up materials, solvents.
Exactly. A logistical nightmare. Not to mention the environmental cost, all the waste generated. It just wasn't feasible.
Which brings us to the really fascinating part. They didn't try to test them all. They moved from the lab bench to the computer.
They did indeed. This is where the innovation really shines. The Virtual Ligand-Assisted Screening Method, VLAS. This was developed by Associate Professor Wataru Matsuoka and Professor Satoshi Maeda, part of the WPI-ICRDD team there.
VLAS, virtual ligand-assisted screening, what does it actually do?
It's basically a computational workflow. It's designed to speed up finding the right conditions for catalytic reactions, specifically by screening potential ligands. It calculates how a given ligand would affect the reaction's crucial energy points, especially the transition state that high-energy hump the molecules have to get over to become products.
So instead of mixing chemicals and hoping, VLAS runs simulations. It models the physics and electronics of the reaction.
That's the core idea. It models the interaction between the ligand, the catalyst, and the substrate, the ketone in this case. For this specific problem, they used VLAS to look at 38 different phosphine ligands, chosen to represent a wide range of structures.
38. Okay. Still a lot, but way fewer than thousands.
Much more manageable computationally. And VLAS calculated two key things for each ligand, connecting them directly to that problematic BET pathway. First, its electronic nature. Is it electron-rich or electron-poor? Second, its physical size, its bulkiness. How much space does it take up around the palladium?
So it's modeling both the electronic push-pull and the physical crowding, trying to find the combination that makes it hardest for that electron to jump back.
Exactly. It's predicting which properties would build the highest barrier against B, essentially creating a predictive map of success before they even picked up a test tube.
That's incredible. And the result of this computational work.
The result was this focused prediction, almost like a heat map, showing which types of ligands should work best.
And this is where the efficiency payoff is just huge. Based on that VLAS map, they didn't test all 38 ligands they modeled. How many did they actually take into the lab?
Just 3.
3. Down from potentially thousands, modeled 38, tested only 3.
A massive reduction in experimental effort. And it worked. Right out of those 3 computationally selected candidates, they found one that did the job perfectly. L4.
L4, and that is?
It's called tris-4-methoxyphenolphosphine. A bit of a mouthful, but its properties were exactly what VLAS predicted would be needed.
And what's special about it?
It's very electron-rich. According to the VLAS calculations, and confirmed experimentally, this electron-donating ability helps to stabilize things just enough when the palladium is excited by light.
So going back to the short circuit analogy, L4 acts like putting a resistor in the system, slowing down that immediate electron backflow.
That's a good way to put it. It doesn't completely stop it forever, but it slows down that BT process enough. It increases the energy barrier for the electron to jump back. That strategic choice, guided entirely by computation, effectively suppressed the back electron transfer that had plagued earlier attempts.
And suppressing B meant success.
Yes. Finally, they could generate those elusive alkyl ketyl radicals from common alkyl ketones reliably under mild conditions and get them to react further with high yields.
They solved the decades-old problem, unlocked that reactivity.
Absolutely. As the source material puts it, this gives chemists facile access, easy access to this really valuable type of reactivity. It's not just a niche discovery, it's a practical tool others can now use.
It really feels like a...
I agree completely. When you step back, this research, which was published in a top journal, the Journal of the American Chemical Society, it really demonstrates how computation isn't just helping chemistry anymore, it's starting to lead it. Going from thousands of possibilities down to just 3 successful experiments, that's transformative. It saves immense time, resources, reduces waste, and accelerates the path to new molecules, whether for medicine or materials. It really is a shortcut to innovation. Thinking about that acceleration, what stands out to you about how these computational tools might fundamentally change how we even train chemists in the future, or what their day-to-day work looks like?